So why does radioactive decay occur? And what can we do to maybe take advantage of this? Physicists looked at the masses of these nuclei, right? Nuclei are comprised of protons and neutrons. The electrons are in orbit around the atomic nucleus, but this is nuclear physics now, so we're not going to consider the electrons, except in the few cases where we get beta decay or electron capture, where the electron will enter or leave the nucleus. But let's ignore that for now and just look at the nucleus. It's made of protons and neutrons. So if you look at the sum of the mass of the protons and neutrons that make up a nucleus, like for instance, the simple helium. Helium-4 is comprised of 2 protons and 2 neutrons. So if you weigh a proton and you multiply that value by 2, because there are 2 protons in the helium nucleus, and you weigh a neutron and you multiply that by 2, and you add them together, that should be the total mass of a helium nucleus. But it's not. A helium nucleus weighs a little bit less than the sum of the masses of the parts of the helium nucleus. There's a little bit of missing mass there. That missing mass goes into the binding energy of the atomic nucleus. Which means that if you want to take apart a helium nucleus, you have to add energy to it to pluck away these protons and neutrons. So, the mass difference is equal to the number of protons, Z, atomic number, times the mass of each proton, right? Proton mass is universal, plus the number of neutrons, so the atomic mass minus the mass number minus the atomic number, gives you the number of neutrons, times the mass of each neutron. And again, the mass of a neutron is a ubiquitous object, so all masses are the same. Add up, so this is the mass of all the parts of the nucleus, and then subtract the mass of the nucleus itself. What does a helium nucleus weigh? What does an oxygen nucleus weigh? What does a lead nucleus weigh? Gives you the difference in mass between the final product, the nucleus, and the things you used to build it. Well, Einstein said E equals mc squared, so the binding energy is the mass difference times c squared. So you just take delta m, I plugged it in here in the square brackets, times the speed of light squared, and that tells you the binding energy of a nucleus. Oh, great. So we can figure out how tightly bound nuclei can be. Why do we care? Well, we can actually look at how tightly bound a nucleus is compared to other nuclei. Which is the most tightly bound nucleus? Is it helium? Is it uranium? Is it lead or argon or krypton, xenon? I say krypton, I'm thinking of Superman, but it is actually a gas as well. So if you divide the total binding energy by the number of nucleons you have, by the atomic mass number, A, you get the binding energy per nucleon. And something interesting happens. I'll show here a graph to my right. This is a graph of the binding energy per nucleon on the y-axis as a function of atomic mass, or atomic number, I should say, on the x-axis. See how the binding energy is low on either end of the graph. It's significantly low on the left-hand side, where you have hydrogen and helium and so on. It peaks around iron and nickel, and then it slowly descends when you get out to the higher atomic mass numbers, or atomic numbers. So what this is saying is the most tightly bound nucleus you could get is basically iron. Iron or nickel. So if you have a smaller atomic number, or on the left-hand side, if you're hydrogen, if you're helium, if you can combine those light nuclei together, you can create more tightly bound, heavier nuclei and release a little energy in the process. This is called nuclear fusion. When you fuse light nuclei to create heavier nuclei, you release energy in the process. This is a power source. This is what actually powers the sun right now. hydrogen is turning into helium in the sun. 600 million tons a second of hydrogen gas becomes helium. A little bit of mass difference between those products. The 600 million tons of hydrogen becomes a little bit less than 600 million tons of helium. And I think it was 600 or 300. I'm trying to remember from memory. Let's say 600 million. Tons of hydrogen becomes a little bit less than 600 million tons of helium. And in that process, a small amount of energy is released. That's what powers the sun. If the sun were powered by coal, if you had a giant mass, the sun were pure coal, assuming we can get oxygen to it, the sun would only burn for 10,000 years. Chemical energy is actually quite weak, because chemical energy is electrons changing energy states. Nuclear energy is the atomic nucleus changing energy states. You get much more bang for your buck in the atomic nucleus. Nuclear power is far, far, far more powerful than chemical power. An example of that is a chemical bomb versus a nuclear bomb, right? Nuclear bombs are far more powerful, far more dangerous. Well, nuclear fusion only works up to the point where you hit iron. You cannot fuse iron together and expect to release energy. In fact, it takes energy to fuse iron with anything. So then, moving to the way right side of this plot, we can see uranium, plutonium on the far right side. If you break up those massive nuclei, you move closer to the left side of the plot, closer to iron, and you again release energy. That's called nuclear fission. And we'll talk more about nuclear fusion and nuclear fission a bit later. Nuclear fission is breaking up a massive nuclei like uranium or plutonium into smaller nuclei, lighter nuclei, and release energy in that process. And again, up to iron. If you try to break up iron that would require energy, it doesn't release energy. So iron is the most stable nucleus. Fusing up to iron or fissioning down to iron is possible. Nuclear fission does not release as much energy as nuclear fusion for a given mass. You can see that hydrogen is way down here at the bottom of the plot. Uranium, way on the right-hand side, is more tightly bound. But it's easier, and we could do it in the lab, it's easier to actually create a situation where nuclear fission occurs to generate power than nuclear fusion.